Now, people were not sure what really was being transferred. What is it that's going from the stove to the water? Why is it that the stove, if it's not plugged in, is getting cooler and the water is getting hotter? They just decided to call it the caloric fluid. They imagined there was a certain fluid which is abundant in hot things and not so abundant in cold things. When you put hot and cold together, this magical fluid flows from hot to cold, and in that process heats up the cold thing. And they decided to measure it in calories. And so you have to define what a calorie is. In other words, you want to ask, how much heat does it take to heat this bucket of water? And the rule they made up was, we're going to define something called a calorie, where the number of calories you need is equal to the mass of water times the change in temperature. And that's going to be calories. In other words, if I had a container with 10 grams of water and the temperature went up, I'm sorry, this is mass of water in grams. If you have 1 gram of water and you did something to it and the temperature went up by 7 degrees, you have, by definition, pumped in 7 calories. If this was a kilogram of water, this will be called a kilocalorie. So sometimes I use grams and calories, sometimes I use kilograms and kilocalories, but the definitions are consistent. If you put a kilo in the gram, put a kilo in the calories. Okay. Now suppose you say, I don't want to just talk about water, I want to talk about heating something else. Maybe I want to heat a gram of copper. So then you write down the following rule. The amount of heat it takes to heat up anything. Pick your own favorite material, gold. Then the amount of heat, I think we can all appreciate, must be proportional to the amount of stuff you're trying to heat up. That's our intuitive notion. If you got one chunk of gold that takes some number of calories, you have a second identical chunk. By definition, that should take the same number of calories. If you put them together, it is clear that whatever this calorie fluid is, you need double that. So it's got to be proportional to the mass of the substance. And it's got to be proportional to what you're aiming for, namely an increase in temperature. But this is true for any substance, whether you're heating copper or wood or gold. No matter what you're heating, it is true the heat needed is proportional to the mass and to the temperature. So what is it that distinguishes one material from another? We put a number here, and that number is called the specific heat. The specific heat is a property of that material. You got to understand certain formulas will depend on certain parameters in a generic way and some things that depend on the actual material. In fact, that's a similar quantity. I mean, maybe I'll take a second to tell you. If you go to liquids that I said were expanding, you can do the same thing. Take a rod and start heating it and ask, how much will it expand if I heat it by some amount delta T? What will it be proportional to? Can anybody think of what it may be proportional to? Yes?
Original length.
Depends on the original length of the rod. Now, why is that? Why do we think it's got to be proportional to the length of the rod?
Because it's expanding based on what it had before.
Yeah, it's based on what it had before. Yes?
Well, each section of the rod expands by a certain amount, so...
That's correct. I think one way to say that is, take a meter stick, it expands by some amount, put another meter stick next to it, that expands by the same amount, by definition of identical things. That for the 2 meter stick will expand by twice as much. So we put the length of that. So no matter what you're heating, a block of wood, block of steel, this is true. But then the fact that heat has different effects on copper versus wood is indicated by putting a number here. That alpha is called the coefficient of linear expansion, and that depends on the material. These are true no matter what you're heating. So these specific numbers, these coefficients, these alphas that come in are going to come in all the time, so you should get used to that. Here's another one. Let's play this game one more time. We can ask how much does the volume of a body change when I heat it? Well, the change in the volume, again, will be proportional to the starting volume times the increase in temperature. Then you put another number, that's called the coefficient of volume expansion. And that depends on the material. So if you take copper, copper will have a certain alpha. Iron will have a different alpha. Wood will have a different alpha. Each material will have a different alpha. This is the property of the material. If you say, well, I had something, and when I heated it up by 1 degree, it increased by 9 inches, another one increased by 2 inches, is it clear that the first one expands more readily? It's not, because the first one could have been a mile long, second one could have been a foot long. So you have to take out certain factors that are universal, and the rest of it you put into a property of the material. Similarly, when you come to specific heat, you ask how much heat does it take to heat some object. It depends on the mass. It doesn't matter what you're heating. It depends on the increase in temperature, because that's the whole purpose of adding heat. It's always going to be linear in the delta T. This one is a property of the material, and by definition, C equal to 1 calorie per gram or 1 kilocalorie per kilogram for water. Once you've got, so remember, 1 calorie per gram for water is a definition. Once you define water to have a specific heat of 1 calorie per gram, you can define specific heat for other materials by the following process. So what do? You take a container with some water in it. Let's assume the container has 0 mass, so I don't have to worry about it. It's an approximation. If you're worried about that, take a huge container so that the volume of water dominates the surface area of the container. Anyway, container is neglected. You got some water. This water is at some initial temperature T1. And I have some new material, lead, and I want to find its specific heat. So I take the lead in the form of pellets, and I heat the lead pellets to some temperature T2. And I drop these guys into this water. That'll be an example where initially the lead is in equilibrium, maybe on a furnace at temperature T2. Water is in equilibrium, maybe in the room at temperature T1. Then I put the pellets into the water. There'll be a period when the temperature is not defined. Then soon they will settle down to some common temperature called T. We will now postulate, this is a postulate or a law. The total change in Q is 0. In other words, if Q is lost by one body and gained by another body, the loss and the gain must equal. It's the new law. Now you can make up all the new laws you want. You don't know if they're right, but this is the law you first make up. In that case, what can you say in this particular problem? In any of these heat problems, I urge you to draw the following picture. Here is one temperature. Here's another temperature. Here's the final one, which we don't know. But we can measure. Put a thermometer and measure it. Then you say the mass of the water times specific heat of water, which is 1, times delta T, which is the final temperature minus the initial temperature. Ditto for the lead pellet, mass of the lead. Lead has got a symbol Pb, times specific heat, which I don't know, times the change in temperature, which is T final minus T2, is equal to 0. The sum of all the MC delta T's is 0. This is the gain of heat of the water. This, if you work it out, will be a negative number, because you can see T final is below initial T. This will turn out to be negative, and the positive and negative will add up to 0. So what is it you don't know? Well, you know the mass of the water. Specific heat of water is 1 by definition. T final and T1 are measured by thermometers. Mass of lead is for you to measure. These are known. You can find C. So this is a birthday present for you guys. If you ever see this in an exam, jump on this first, because you've been doing this in high school, and I know kids love this kind of calorimeter problems. Yes?
Looking at the volume in that
equation expands linearly, but wasn't the problem with the liquid, measuring liquid change in volume, that it didn't expand linearly?
Yes,
So,
that's correct. So the real point is, if everything expanded linearly, we won't have the disagreement between different thermometers. So it turns out, to an excellent approximation, the change in length is proportional to the length. But it's not exactly proportional to the length. There will be terms involving higher powers of length. Not only that, specific heat of materials is also not a constant. We say specific heat of water is 1. Turns out, at a certain temperature range, it will be 1. At a different range, in fact, it's not quite 1. I told you long back, everything I tell you is wrong. The question is, how many decimal places do you have to go to before you unearth my fallacies? Specific heat materials is not a constant. It's a big industry calculating the specific heat of materials starting from atoms and quantum mechanics. So none of the things treated as constants are ever constants, including those alphas and betas. I can always fudge it by saying alpha itself may depend on the temperature, and also the dependence on L may not be linear. But you should also look at dimensional considerations and say, if it's not L, if you want to put an L square as a correction to the formula, to match the units, the L square has to be divided by another length to keep the units. What other length do we have? It may turn out to be the interatomic spacing. So once the atomic properties come into play, then you can find ways to calculate corrections. So all these laws are, in fact, very tentative and approximate. These are pretty ancient physics. I think the way I do the physics course here, sometimes I'm in the 1600s, sometimes in the 1400s, sometimes in the year 2000. So it's going back and forth. This is way back when people did not even know about atoms. So they were trying to do the best they can. And what you found empirically is that once you found a specific heat for lead, right, you solve for it, then you can do another experiment using that value, and you find if you use the right values, delta Q does add up to 0. Again, when you say adds up to 0, adds up to 0 to a very good approximation during that epoch. Another epoch, when people do more and more accurate experiments, everything gets shot down. In fact, specific heats of all materials seem to go to 0 when you approach absolute temperature. You have to understand the laws of quantum physics to know why that happens. So this is a period when people are probing temperature ranges which are around room temperature or boiling and freezing point water, which is a very narrow window in temperature. If you look at the history of the universe, you've got incredibly high temperatures near the Big Bang. And even now, the rest of the universe is bathed at some temperature that happens to be very, very low, which is near 3 degrees. It's called the black body radiation from the Big Bang. So the temperature of the universe goes through huge ranges. And only when you probe different ranges, you see different physics. If you come to Sloan Lab, you can go to temperatures way below 1 degree Kelvin or 100th of a Kelvin. And we heard a talk last year, physics at 1 billionth of a Kelvin. So you want to cool them and cool them and cool down. But 0 degree Kelvin, see, there I go. 0 Kelvin is a barrier we're not able to cross, just like the velocity of light is something we're not able to cross. These are all big surprises. The fact that velocity has an upper limit, not obvious even to Newton. Why not? Why not put rockets on top of rockets? Likewise, why not build better and better refrigerators? The reason you cannot go below 0 is when you go to 0, all the mechanical attributes like pressure simply vanish, and they cannot have negative values. You will see more about this when you understand heat in greater depth. Anyway, right now, delta Q equal to 0 is the rule you use. I'm sure you guys know how to do these problems. Now, there's a little twist that comes in. I just want to mention that to you. The twist is the following. So I take some ice. Ice, by the way, is not always at 0. You know, you can go below 0. Your refrigerator is several degrees below, several tens below 0. So let's take ice, and let me measure. I take this container. I put some ice at, say, minus 30 degrees. I've gone to centigrade now, so we can relate to ice. And I put it on some source of heat. And I watch how many calories are coming in. Let me arrange a device that will pump in a fixed number of calories every second. So as a function of time, I'm expecting the temperature of this to go up. Do you understand that? In every second, I get some number of calories. And those number of calories are going to produce for me mc delta T. M and C are constants. So delta Q is proportional to delta T. But if you divide both by the time elapsed, then the rate at which the temperature rises will be the rate at which the heat flows into the system. If heat is flowing at a steady rate, temperature should rise, and indeed it does. Temperature of the ice goes from -30